Sweet. I welcome everybody back for another live stream. What I am going to cover today is kind of preparing for some solving trigonometric functions. So I was gone today inside of my school. And so what I did was I kind of prepared a little document to help my students prepare for our upcoming lesson. So I'm teaching this chapter a little bit differently than I've taught before. We are, in my class for pre-calculus, we're entering in analytic trigonometry. And rather than getting into identities, simplifying, verifying, and then the sum and difference, double angle, half angle, blah, blah, blah. And then usually what I used to do is always end with solving trigonometric equations. Well, this year I am deciding to flip that kind of script around and actually start with solving trigonometric functions or equations first. And I'm going to kind of see how that goes. Maybe I'll do that next year again, or, we'll just kind of see what it is. That's kind of the joy of being a teacher is, trying things, seeing better ways for things to make sense to students, because I feel that the last chapter that we did, we ended with inverse trigonometry, and I feel like that's a really good jumping block to get into solving trigonometric equations. Obviously, we're not going to be able to get to all of the stuff as far as applying the identities to solve, so we'll just kind of we'll come back to that stuff, later. But before I go ahead and get started here, I just want to get some things on my end, a little bit of housekeeping stuff. Make sure. All right, I do have some people that have joined. Thank you very much. Good to see you guys. Vasanth, Hacking Made Fun, Esmeralda, and Delta. Good to see you guys again. Nice Blue Eddie. Yes, I did decide. I figured, what, if I'm going to be doing this, I might as well. Hopefully I have some good audio for you guys. I think there's nothing worse than, trying to watch a video and just there's really, really bad audio, which I am obviously guilty of in some of my older videos. I didn't really care so much about the audio. I would just I was teaching my class. And so I would just, either didn't use a lavalier mic or I wouldn't really check the volume all the time. And, part of that is because my real main goal was just to teach my students. And obviously the recording was, the byproduct. Hey, Jet Butt, how are you? Actually, Sony, Paish. Sorry, I'm badgering your names, but it's okay because I badger my own students' names, so they're kind of used to that. So sorry about that if you want to give me. Barnacle True North, happy Monday to you. Good to see you join on the live chat. Or I'm sorry, the live stream. And what we're going to do is just kind of get you things. Now, I do want to get into some Q&A. The little worksheet that I have should not take too long for me to go through because, again, it is really a review for my students. So I'm not going to get like in depth going through everything. So I will kind of move along a little bit through this. And then hopefully at the end, I can kind of work back through on the chat for you guys. And if you guys have any questions on anything that you're going over in your class, I would love to kind of, help you out and see if I can lead you in a direction that is, will get you going. So what I'm going to do is I was trying to look at this and see, okay, there we go. Let me just pop out the chat. So now, one of the reasons I had a couple of people ask me why I do not pop out the chat in my live stream. And one of the reasons for that is because I can't really moderate what you guys are saying all the time. And obviously on some of the things on the chat are not really that appropriate. So that has been kind of the reasons that I do not show the chat. But I can see it. I have a nice little pop-up here on my end, and I will make sure I go through it. So if you do have any questions, please make sure to add them into the chat. And what I'll do is once I'm done with going through this worksheet, I'll kind of answer some questions that I can help you guys out with. So first of all, I just want to kind of show you guys a little bit what I'm working on. So this is it's basically kind of like day one, analytic trigonometry, just some kind of essential skills that you would need to know, as we're getting into this unit. And again, as I mentioned, I'm not starting with identities, which is something typical I've always done, getting started with identities. But what I've noticed with the students is a lot of times they have a hard time transitioning with the identities. Even though I, relate a lot of the stuff that we've done into identities, it's still kind of like a mental jump for the student. So I decided, I'm going to try to maybe make a mental jump to the solving and make sure that they're really still comfortable with stuff. And then we'll kind of get a little more deep into the identities. So what I decided, some essential skills that I feel like students need to know for solving trigonometric equations. would be solving just general equations, linear and quadratic. Making sure you can evaluate using the evaluate the inverse trig functions. So again, that's using the restriction on the domain, which is not as important when we're dealing with solving for like all solutions or solutions between 0 and 2 pi. However, that at least gets you started remembering with that. And then also talking about the asymptotes. And that's really just kind of important when we start writing like all the solutions and understanding how the period and multiple solutions or multiple asymptotes kind of occur. So good to see you, Connor and Delta 280 again. Arrived winner. It looks like you have, I need some help with my homework and about one solutions. Well, I will be getting onto, I'm hoping to try to go live maybe tomorrow or maybe sometime again this week once I assign some kind of homework for my students to do. My goal is kind of like what I've done in the last couple of weeks is to do those homework problems. So once I actually start getting into more problems that we're doing, I'll answer questions that are more related. But for this video, what I'm going to do is just kind of focus on preparing the students for it, just, kind of going through these questions and not really talking so much about solving trigonometric equations. However, as I mentioned, that is something I'll get to at the end. So, hey, Clumpy, how are you? All right, ladies and gentlemen. Well, while I get started, and again, this is probably take me, I don't know, it's 8:37. So I'm hoping to try to be done here in about 15, 20 minutes as I kind of speak this. Before I get started, though, I would love to kind of see where you guys are watching from and also what kind of course you are currently taking. That would really help me as far as getting a better idea as far as my audience on this Monday evening. For me in Eastern Standard Time, it is 8:37. So if you guys just want to comment below, just kind of let me know where you are watching from as well as what class you're going. I'm going to go ahead and get started. I'm not going to pay attention to the chat, but please make sure you enter that in. And as well as if you have any questions, go ahead and let me know. All right, so let's go ahead and get started here, getting into solving equations. Now, as far as solving equations, this should be something, hold on, let me move my viewing window up here so I can see. All right, perfect. Could I not move that open? No, I can't. I can make that bigger. Okay, put that down there. There you go, that reminds me that it's non-viewable. Okay, so as I'm kind of working through this, guys, we're looking into solving equations. And again, guys, this is, I know something pretty basic for the majority of you. So I'm just going to kind of, go through this. But again, the main important thing is just understanding your inverse operations. And that's what I really want students to kind of get from this is, understanding that when we're trying to solve for x, we're trying to undo the operations. So you can see our x is being multiplied by 2 and it's subtracted by 1. So we just want to isolate the x. So the first thing we're going to do is undo. I don't know why I am undoing a plus, but we're going to undo subtracted by 1, so we're going to add a 1 to both sides using the properties of equality. So therefore we have 2x equals 1, divide by 2, using the division property of equality, and then x equals 1/2. And again, the whole idea of the equation that I want to go through these problems again for is if we were to replace x with 1/2, that would make this equation true. And I don't really have the I guess I can put over here, again, if you put in 2 times 1/2 minus 1 equals 0. 2 times 1/2 is 1 minus 1 equals 0. And therefore we have an identity. So right now this is what we call a conditional identity. We're solving for x to make that identity true. And now this is an identity. And I'm using this language because that's the language that we're going to be using in this analytic trigonometry chapter. All right, so the next one here, we have 3x squared. So we want to isolate the x, get the x all by itself. Now we see that two operations are happening to the x. We see it's multiplying by 3 and it's being squared. Well, by following the reverse order of operations, we're going to want to divide by 3 first. And therefore, we're left with x squared equals 1/3. Now, to undo squaring, we're going to want to take the square root. And just remember when you're introducing the square roots, let's actually use blue. Remember when you're introducing the square root, you have to make sure you include the positive and the negative version of this. Now, I am going to do a little bit of math or a little bit of simplifying here. So we have to make sure we include plus or minus the square root of 1/3. And this, usually with radicals, tricks up a lot of students. And one thing as far as like simplifying this, when you're looking at an answer choice, more likely not, you're not going to see plus or minus the square root of 1/3. But usually what we can do is we can take the square root to the numerator and the denominator. That's going to equal the same thing. So you could say plus or minus the square root of 1 over the square root of 3. Obviously the square root of 1 is just 1, so I could just write a 1 up there. And then if we want to rationalize the denominator, or the problem or our teacher says you need to make sure that the denominators are rationalized, there's no square root in the denominator, we're going to want to multiply by the square root of 3 on the top and the bottom. So therefore, our answer is going to be plus or minus. So again, remember square root of 1 is 1. So 1 times square root of 3 is the square root of 3 over the square root of 3 times square root of 3 is going to be, now when you're multiplying radicals, you just multiply the radicands together and then take the square root. So square root of 3 times square root of 3 is square root of 9. Square root of 9 is going to be 3. And again, you could plug this back into your equation, and you're going to go ahead and make the equation true, or the identity true in this case. So anyways, moving on to the next one. So now we have again another x squared, and then it's being multiplied by 2. The only difference here is now we're going to be subtracting by 1. So again, we'll just follow the same plus. First thing we want to do is always undo addition and subtraction first. So therefore we have 2x squared equals 1. Divided by 2. I'm getting a little bit better with this this nice little thing, but it's still a little tricky. So divide by 2, and therefore I have x squared equals 1/2. Now again, introduce the square root on both sides. And then you guys can have x squared equals plus or minus. Again, I can just rewrite this as 1 over the square root of 2. And if I go ahead and rationalize the denominator here, multiply by the square root of 2 over 2. Now again, notice I'm rationalizing the denominator here. I'm multiplying by square root of 3 over 3. Here I'm multiplying by square root of 2 over 2. Again, you want to multiply by the same value as what your square root is. If there's more numbers there, you don't really need to be concerned about it. And then my final answer is going to be, make sure I'm not running off. Move that up a little bit. Oh, I have more answers over here. Good thing I don't want to forget about those. That's going to equal square root of 2 over 2. Crap, that's plus or minus. Got to make sure you include that. That's one of the more common mistakes that I see with my students, is they will, do it, or they'll just forget about that plus or minus. But that's very important, extremely important, especially in this chapter for solving trigonometric functions, because you're not going to have all the solutions if that's going to be the case. And then this last one, it has a square root, but it's really not any more difficult here. All we need to do is just kind of say, all right, well, let's just undo what's happening to the x. So my x is being subtracted by a square root of 3, so let's add a square root of 3. And therefore, I'll have 2x equals square root of 3. And then to undo the multiplying by 2, I'll just divide by 2. And therefore, x equals the square root of 3 over 2. Okay, so now let's kind of get into some those are quadratics too. But now let's kind of get into ones that are kind of dealing with a little bit different, just with, something using the square root method or a linear equation. Here, again, remember that when you have a product of factors equal to 0, then you want to test both those factors equal to 0 to identify the solutions, because if one of these factors is equal to 0, then the whole equation is equal to 0. So that comes from the zero product property. A times B equals 0, therefore A equals B, or A equals 0 or B equals 0. Sorry, I'm misstating that. So anyways, let's kind of use a different color here. So whenever we have a product equal to 0, now again, it's very important. This product has to be equal to 0 to apply the zero product property. I'm just going to set each factor equal to 0. X minus 1 equals 0, and therefore 2x plus 1 equals 0. And now by doing this, it's much easier for me to go ahead and just get my answers. Now to speed this up a little bit, I'm just going to write in my answer as x equals 1 and x equals negative 1/2. Now, once I start speeding things up, I'm going to do my math in my head, and I'm also going live, and I'm also talking. So if I start making a mistake or whatever else, I will go ahead and check, my chat every once in a while as I'm going through this. So please, let me know if I make a mistake, because obviously I'm doing like 4 or 5, 4 things at the same time. Anyways, again, we can plug these values back into these equations. You can see 1 makes that 0. 0 times 2x, or plug 1 in there, so 2 times 3. So 0 times 3 equals 0. And if I plugged in a negative 1/2 into here, that makes that expression 0, and 0 times anything is going to be 0. So that works. Now, in this one, we can look at this x plus 1 squared. Now, I would not use the zero product property here, but I just want to write this out because a lot of students forget this. They always want to write x squared plus 1, and it's not. When this is expanded, it's x plus 1 times x plus 1, and that's very important. So make sure you understand that. So therefore, if you did the zero product property, you would get the same answer twice. And that's kind of interesting. You're like, and if you remember in our polynomial unit, that was called our multiplicity. But anyways, I won't use the I won't expand that. You could, though. There's nothing wrong with that. But what I would do is I would just undo the squaring first. So if I square root and square root. Now, again, what happens to the plus or minus, right? Because we have that plus or minus. Well, 0 is not positive or negative. So it doesn't really matter to do the plus or minus. 0 is 0. So therefore, we're just going to be left with x plus 1 equals 0. So therefore, x equals negative 1. So technically, if we're looking at a function, the 0 is negative 1. Remember, it has a multiplicity of 2. Just to kind of review for my students, remember that means that if we were going to look at the graph of that function, it is bouncing at that 0 of negative 1. However, for this chapter, we're not worried about that. I just wanted to kind of relate some things for you guys. All right, so now let's get into a couple factoring ones. Nobody likes factoring, right? Well, when we're solving factoring, I put this equation up here because I knew it was probably going to trick a lot of students. They're looking at this and they would immediately just want to start factoring this. But again, guys, remember our idea of factoring is that we want to have it in a factored form. We want to have a expression times another expression equal to 0. So first of all, this is non-factorable as it is, but we want it to be set equal to 0. So we're going to want to do a little bit of math here first. Subtract 1 on both sides, so therefore we have x squared, make sure I'm okay, x squared plus 2x plus 1 equals 0. Now I want to look into factoring this and say, all right, what two numbers multiply to give me positive 1 and then add to give me 2? Well, guess what? That becomes x plus 1. Oh, that was a bad equation. That was the exact same one as the other example, just rewritten. But either way, so that turns into x plus 1 squared equals 0, which again, now we can just, kind of know this answer. We know our solution is x equals negative 1. And again, just a reminder, you can always plug your value back in to make sure that that's going to give you the correct, solution. That's going to make the identity true. If you plug in negative 1, the left side is going to be equal to the right side, right? And that's basically the definition of an identity. All right, so now here's a good one. This one, because we have this a here. And usually nobody really likes trying to factor when we have a. But we do have it set equal to 0, so that's good. Now, I'm going to do this one. I'm not going to work this out like in some crazy math because we should be fairly comfortable with factoring. At least in my class, we should be at a point where we kind of understand that we know that the first two factors, the 2x times the x, is going to give us 2x squared. We want to figure out what two numbers are going to be multiplying to give me 1. But remember, when I use this distributive property here, I'm going to be multiplying by 2 here. So what I see here is I want to figure out two numbers that are going to give me 1. Well, that has to be, positive 1 and positive 1, or negative 1 and negative 1, right? That's the only way that's going to work. But I know that if I'm going to be adding them to give me a did I do this wrong? I think I may have set this problem up wrong. I think this is supposed to be a negative 1. Let me check here. So anyways, to give me a negative, that should be a negative. And then to add that, that was supposed to be a positive. Yep, I made the problem wrong. Dang it. So my bad. So let's go. Let's fix that. There we go. It's like you guys couldn't even tell, right? This is supposed to be negative. That was at least my idea. Sorry about that. So anyways, that's allowed. Trust me, it's allowed. I made up the problem wrong. Sorry about that. So anyways, so now when you go and multiply, the 2x times x is 2x squared. 1 times negative 1 is negative 1. And 2x times 1 is negative 2x. Plus 1 times x is going to be a negative x. So therefore that works. Then I can just go ahead and apply the zero product property. So 2x plus 1 equals 0. And x minus 1 equals 0. So therefore, x equals negative 1/2, and x equals 1. Hold on 1 second. I'm going to take a quick little intermission. My wife is texting me. baby is crying. So my wife is being very lovely and allowing me to live stream right now while the baby is crying. So, all right, so let's kind of get through this, and then I'll go ahead and take care of my baby, and then I got to prepare for tomorrow. So it's going to be a late night for me, but that's okay. Kind of used to it. I didn't have school today because I was in jury duty, but they didn't select me, so I don't have to go to trial, which is good, bad. I kind of wanted to do it. I thought it was going to be something kind of interesting, and I want to kind of do my little civic duty for it. But in the end, I know it's also going to take me away from school, and it's very kind of like long and boring sitting in the courtroom. So, yeah, I was just kind of, whatever happens, I'll accept. All right, so let's kind of go into the evaluating the trigonometric functions. Remember, guys, evaluating the trigonometric functions is all about understanding the unit circle. So I'm just going to do a quick little sketch of at least the first quadrant here. That's bad. Let's do that line right there. Let's delete that one. No, wrong. There you go. Okay. So therefore, let's say this point is, that's going to be 1/2, comma, square root of 3 over 2. This point is square root of 2 over 2, comma, square root of 2 over 2. And this point is square root of 3 over 2, comma, 1/2. Now, not going to go into too much detail, but again, remember this is pi over 6 or 30 degrees. The next angle is pi over 4, 45 degrees. The next angle is pi over 3 or 60 degrees. And then we also have these points, which is pi halves or 90 degrees, which is 0, comma, 1. And this point, which is 0 degrees or 2 pi, is 1, comma, 0. All right, so let's kind of go back up and look at this. So the first equation is basically saying when you're looking at the sine inverse of square root of 3 over 2, the main important thing I really wanted to go over these problems again with is really understanding what the question is asking. This question, sine inverse square root of 3 over 2, is basically saying the sine of what angle is equal to the square root of 3 over 2. What angle, when I take the sine of that angle, gives me the square root of 3 over 2? Well, remember when we're looking at the unit circle, sine represents the y-coordinate. It's still opposite of hypotenuse, but since the hypotenuse is 1 on the unit circle, it's just the opposite side, which is the y-coordinate. So let's go and see if we can find the y-coordinate here of square root of 3 over 2. And yes, we can. So that is our angle. And again, by knowing your angles of the unit circle, that is going to be the angle of pi over 3. So the answer can be done as quickly as that. So we can just say the answer is pi over 3. Now, when is the cosine inverse equal to the square root of 2 over 2? I'm not going to scroll back down, but once I do, you can obviously go ahead and see that this angle is just going to be pi over 4. Again, this could be looked at as cosine of what angle equals the square root of 2 over 2. And that angle is pi over 4. And again, sorry, I should probably go into this. Again, these are identities. I mean, if you could plug this in, you created a conditional identity, and you're finding basically the condition that makes that identity true. And if you look at this, when I plug that value in, I have an identity. The left side is equal to the right side. They look completely different from each other, but they're equal. All right, and that's kind of the main driving point that I'm trying to bring across here. For the next one, this tangent inverse of square root of 3 over 3. Now, this one actually isn't as fun. So we want to make sure we kind of go over how do we find those points. And I'll go to the answer, which is right here, because I've been doing this for so many times, and I want students to be able to say, like, this is what I want you to, kind of know. All right, if I look at tangent on the unit circle is y over x. So if I take 1/2 over, this isn't really equal, so I don't know why I'm writing that, over the square root of 3 over 2, you can multiply by the circles or see that the 2's divide out. So therefore, you're left with 1 over the square root of 3, which rationalizing the denominator equals square root of 3 over 3. And again, I'm going a little bit quicker because I have been doing this for my class, so they are very familiar with me working out these solutions. Anyways, what was that angle, though? That angle, so if this one was pi over 3, this angle is going to be pi over 6. Okay, so that one equals pi over 6. Okay, so now let's go ahead and move on to the next one. Sorry. All right, so let's move on to the next one, cotangent inverse of -1. Now, again, when we're dealing with the inverse functions, they're just the I'm sorry, these are, yeah, sorry. I didn't mean the inverse. I mean the reciprocal functions like cotangent and tangent. So when we're dealing with these types of functions, remember that if this one is saying, cotangent of what angle equals -1. Well, remember that cotangent is reciprocal of tangent. So we could rewrite it as tangent of what angle equals 1 over -1. Well, 1 over -1 is still -1. And what angle is when the y over the x is equal to -1? If I was to scroll back that down there is nothing that's going to be -1. However, what we do know is, I'll actually put my work here. In the first quadrant, at pi over 4, I guess I could have done my work here. At pi over 4, we're looking at square root of 2 over 2, comma, square root of 2 over 2. So the negative version of that would be, or one of the negative versions of that would be in the fourth quadrant, right? So it'd be negative pi over 4. And that is going to be our answer. And again, the reason why is because we can't use the other negative version, which would be in the second quadrant, because that doesn't fall within the restrictions of our domain for tangent, which I've talked about in previous videos. Or can we go outside to give us, 7 pi over 4? Because again, that goes outside our domain restriction. So our answer in this case is going to be a negative pi over 4. Now, this one doesn't look that much fun at all. If I take, the secant of what angle equals 2 square root of 3 over 3. Well, another way of writing this, rather than writing cosine of theta equals 1 over this, another way I could do this is I could actually just reciprocate this. I could say cosine inverse of, and just reciprocate it right here, 2 square root of 3. Well, now let's just kind of do this work over here. If I take 3 over 2 square root of 3, and if I go ahead and rationalize that, what I get is 3 square root of 3. 3 times 3 is 3 over 6, which equals square root of 3 over 2. And that's why rationalizing the denominator here, like understanding that skill, is very, very helpful, because now what you can do is you can rewrite this and you can find out, oh, I know where square root of 3 is on the unit circle, where cosine equals the square root of 3 over 2. Cosine equals the square root of 3 over 2 at the angle pi over 6. And again, next time I scroll down to my unit circle, you'll see that first angle there is pi over 6. That's where cosine equals the square root of 3 over 2. All right, and last but not least here is we have the cosecant of -2. Again, if I was going to kind of do this, I could say, well, the reciprocal of cosecant is sine, and I can do this as -1/2. So when is sine equal to -1/2? Well, again, that's going to be at pi over 6. But again, the restrictions of cosecant, of sine, means that it has to be in the first or the fourth quadrant. So if sine of pi over 6 is square root of 3 over 2 comma 1/2, if I want to get to -1/2, then instead of going up pi over 6, I'm just going to go down pi over 6. So this answer is negative pi over 6. And again, that is following the domain restrictions for sine. I didn't have a problem for cosine being negative. Just remember that the domain restrictions for cosine is the first and the second quadrant. So when you're using inverse trigonometry and you have a negative value, you're trying to do the inverse cosine of, remember it has to be in the second quadrant, not in the third quadrant. All right, last but not least is the asymptote. So the main idea I wanted to cover with the asymptote is understanding that these are periodic functions. These functions repeat each other. So even though I sketch the graph with the asymptotes, I'm used to showing you guys what the initial period looks like. The graph repeats itself, and we looked at in my class, we looked at like decimals like that. So I'm just going to kind of sketch here y equals tangent of x. Let's see how quickly I can sketch this without it looking too bad. So the initial period of tangent looks like this. And I told my students before they took their test to make sure that they knew what these parent graphs look like, because I think it's very helpful to understand where the zeros are of these functions, as well as where the asymptotes occur. So cotangent looks like that. And then we looked at the cosecant and secant graph. So y equals cosecant of x. That graph, Now I can't draw a cosecant without at least drawing sine. So you're going to have to bear with me here. I'm going to have to at least draw the sine graph. But I will try to dot it there. We'll just do one period. I don't know why I'm... No, crap. I gotta figure out what to do with that. Okay. It looks something like that. There you go. Close enough. And let's do secant. Y equals secant of x. See, now you're starting to get some of my handwriting in there, which is kind of dangerous. So secant, I'm just going to do the initial positive period as well. So that's 2 pi. So I'll do cosine first. So cosine is going to look something like this. Okay, so these graphs, I'm going to do them in red. So anyways, asymptote, asymptote. Let's do we'll do the asymptotes. Now remember, these asymptotes occur where the graph crosses the x-axis. So that's why it's helpful to know what the reciprocal functions are for cosecant and secant. Cosecant, again, is sine, and secant is cosine. Because then you know where the asymptotes occur. They occur where there's x-intercepts. So this one has asymptotes at 0. And pi. Did I do them at the same? No, I didn't. Dang it. These two have the same asymptotes, basically. These two have the same initial period asymptotes. All right, so let's just do this one. I'll just do green, whatever. And these are kind of like inverted little parabolas approaching your asymptotes. That's at 2 pi. It looks something like that. Okay, so based on knowing these graphs, okay, this is a long time doing these. Based on knowing these graphs, basically what we want to do is kind of go back up here and say, all right, where did the asymptotes occur? So we know that the asymptotes occur here at pi halves for tangent. So, you know, the original asymptote is at x equals pi halves, right? That's the original asymptote of the parent function. However, the period has changed. Now, again, if we look back at the graphs, we know that the period is pi. And the asymptotes occur every pi. So the next asymptote here is going to be at 3 pi halves. So whatever the period is, that's how often the asymptotes occur for tangent. So the period, though, here is not pi. The period is pi divided by b. So we have pi divided by 2. So therefore, the asymptotes in this case is going to be x equals pi halves plus pi halves n. And again, n represents the number of times I could add the asymptotes in the positive or in the negative direction. Now here, what we have is a transformation. So what we want to do in this case is I want to set what's inside my function, x minus pi, equal to pi halves. Okay? And then I want to solve for x, where the new asymptote is. So x equals pi halves plus pi, which I could get common denominators here by just multiplying by 2 over 2. So therefore, that equals 3 pi halves. So my final answer is x equals 3 pi halves plus the period, which again, the period here is pi divided by 1, so it's just going to be pi. So pi n. Okay? For the next one, cotangent, you can see that the cotangent graph has an asymptote at 0. Those are really easy to work with when you have an asymptote originally at 0. So here I have a whole bunch of transformations. You can see that I am changing my period. But again, the easiest thing to do is just set whatever's inside your function, pi over 2, equal to 0, and then go ahead and solve. So when I subtract pi halves, I get x over 2 equals pi halves, multiply by 2 on both sides, and therefore I get x equals pi. So now, where the parent function had an asymptote at 0, the new function has an asymptote at pi. But then we have to incur, well, remember they occur every period. So what is my new period? So again, when you have x divided by 1, just remember, or x divided by 2, just remember x divided by 2 is the same thing as 1/2 x, okay? So when I want to do my pi divided by b, in this case, for this problem, it's going to be pi divided by 1/2. Therefore, I multiply the reciprocal, and I'd get 2 pi, right? So therefore, it's going to be plus 2 pi. 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 2 n. So you're adding in what that period would be. And if you were to kind of count these, you could see that that's going to be at, 3 pi. And, if you add 1, that'd be 3 pi. 2, it'd be at 5 pi, and so on and so forth. Okay, so that deals for tangent and cotangent. Now let's kind of look at the cosecant function. So, Ryan, I'm going to get you some questions here. Let me just kind of finish these 3, and then I'll go back to see if I can answer any questions from you guys. Anything that I've done or anything you guys have in general. So anyways, cosecant. If we look at the cosecant function, that has asymptotes again at 0. So what I'm going to want to do in this case, just give me a second. So when we're looking at cosecant, we have an asymptote at 0. So again, what I'm going to want, real quick, I need to make the mention of this because then I don't need to go back down to this again. When you look at the cosecant function, the cosecant and secant function have a period of 2 pi. However, the asymptotes don't occur every period like they did for tangent and cotangent. Two asymptotes occur within the period. So whenever you're adding that, period n, you want to take that period divided by 2. Okay, so looking at this, what I'm going to do is, hold on, the baby is having a really hard time. So 3 problems. There's 3 problems left. Sorry, guys, I'm not sure if I'm going to be able to get to some Q&A, but if you do write in some comments, I will do my best to go back through and answer anything for you guys. I really do appreciate you wandering in there and seeing, what I can do. And again, if I need to go back out live, to answer your questions, I'll do that. Anyway, so we'll want to go ahead and set 3x divided by 2 equals 0. Okay. And then when we solve for x, we're obviously going to get x equals 0. But again, we want to figure out what the period is. We got to add the period divided by 2, right? Because the two asymptotes occur every period. So first, let's just figure out the period. So the period is 2 pi divided by b, which in this case, b is 3/2. When you multiply by the reciprocal, you get 4 pi thirds. Now, if we take 4 pi over 3 divided by 2, okay, that's really kind of like 1 multiplied by the reciprocal, you get 4 pi over 6, which equals 2 pi thirds. So you could say 0 plus 2 pi thirds, or you could just say the asymptotes occur at 2 pi thirds n. All right, and again, what I'm doing is I'm finding the period, but since the asymptotes don't occur every period, I'm taking that period and I'm dividing it by 2. Now, if you're not familiar with how to take 4/3 pi divided by 2, you can rewrite it as a fraction and multiply by the reciprocal. And then I took 4 over 6 and reduced that to 2/3. I know there's a lot of fraction operations going on in there, but that's okay. For the secant graph, we can see that the initial period starts at pi halves. So if here's 2 pi, there's pi, so that's pi halves, and that's 3 pi halves. So let's use pi halves. Again, what I want to do is take whatever's inside my function. Let's use a different color here. Let's use blue. So I'll take pi halves. No, sorry, you want to take whatever's inside your function. So we'll take pi x equal to pi halves. Then when I divide by pi on both sides, the pi's will obviously divide to 1, so you're left with x equals 1/2. So now my new asymptote occurs at 1/2, and then I got to figure out what the period is and then divide that by 2. So the period is 2 pi divided by b, which in this case is pi, so the period is 2. Take my period, divide it by 2, which is 2 divided by 2, which is 1, right? So therefore, it's going to be 1/2 plus 1n, which again, I don't really need to add 1n. I can just say plus n. And last but not least, guys, and again, I'm trying to get to this because I can hear my baby crying, so I'm just trying to wrap this up really quick. Again, we'll do the same operation, pi over 3 equals pi halves. Multiply by 3 to, what am I doing? X over 3, not, I'm starting to go too fast. Okay, that's x over 3. Now again, to solve for x, I'll multiply by 3 on both sides. Therefore, I get x equals 3 pi, that's a really bad pi, equals pi halves. But then that's the initial asymptote. That's where the first asymptote now has gotten changed because the period changed. But now where do the new asymptotes occur? So you just take your period divided by b, which in this case is 1/3. Multiply by the reciprocal, you can see the period is now going to be 6 pi. Divide that by 2 is going to be 3 pi. So that's going to be 3 pi n. All right. Thank you very much so much for you guys doing all this. I really, really do apologize. I am going to have to cut this short. I see that you guys have done a great job of adding to this conversation, and I really do appreciate you guys doing that. Unfortunately, I am having a little bit of a family issue. My baby is crying and needs me, and my wife cannot get her to fall asleep. So I will plan on I'll plan on coming back tomorrow around the same time, 8:39. So if you guys want to kind of plan on that, if any questions, I'm sorry, I'm just not going to be able to get to them. But if you guys want to plan on coming into there or message me on YouTube, I will try to do my best to make sure I bring them up on the next live stream that I do, either be tomorrow or Wednesday night. So please make sure you guys mention me. And obviously, if you don't want to miss the live stream, all you got to make sure you do is just hit the bell notification on my channel, and that will alert you next time I'm going live. But for you guys that are here, you should know I'm planning on going through around 8:30, 9 o'clock tomorrow. So anyways, guys, I am going to have to end this short. I really do appreciate it. I hope you guys learned some things. I hope you guys helped each other out and weren't just having such a bad conversation. Ryan, I will help you out. I am happy to help you out, Ryan. Just make sure you join tomorrow if that's okay. So anyways, guys, thanks so much for joining, and I will talk to you guys this week. All right. Cheers.